So this is our first Transformative Vertical Flight technical meeting, and it's really a great success. So thank you, Colin, for coming up with the idea, and thank you for the chapter for doing all the hard work to pull this thing together. So in addition to Colin, Barry Lakensmith, Meredith Siegel, Chris Silva, and the whole team for pulling this together. We don't normally have things like this with panels and things, so we're having a little bit of the technical issues. But one thing we are going to do is videotape this, and we're going to put this on our YouTube channel. We've had a series of electric VTOL videos that we've produced. And so this will be a nice addition for spreading the word that this is really happening. This is really exciting. There's a lot of challenges that are going to have to be overcome to make a viable electric VTOL, but we think that they're surmountable eventually. So with that, I'm going to introduce the moderator. You going to stand up here?
I am.
Okay, excellent. So Dr. Ashish Bagai. I had the pleasure of working with him when I was at DARPA and he was at Sikorsky, inventing rotor blades for the X2. And I also had the pleasure of working with him when I was at AHS and he was at DARPA, developing the VTOL X-plane program. So all-around great guy, been an AHS member for 30 years, some amount of time. 28, oh, sorry. Right order of magnitude. And just a real innovator and forward-thinking. I think 5 years ago or so when he came up with the electric VTOL program, people thought he was crazy. And they still think so. They thought he was crazy, this is impossible, and it'll never work, but that's just exactly what DARPA is about, is trying to make impossible things happen, and we're very glad to provide a platform for Ashish today, who's currently at the University of Maryland to lead this panel. So Ashish, thank you very much.
It's wonderful to be here today and to get a chance to say hi to a lot of my ex-colleagues, not only in the government, more recently in the government, but also from academia, University of Maryland. I went to school there and now I'm back there, but also from Boeing, where I spent a short period of my life, and Sikorsky, where I spent a little bit longer period of my life working on a variety of wonderful projects. So I have many thanks and owe many thanks to the community for their indulgence. But I'm here today to introduce you to our panel on emerging urban air mobility. And I would like to start by just pointing out and reminding ourselves that from a remarkable and inspiring WTF moment from a little more than 6 years ago. Do I have the clicker? Is there a clicker somewhere? So that's not my laptop. That's my laptop. That's not the laptop. Okay, next slide, please. Thank you. To the pervasive emergence of electric-powered aircraft with distributed propulsion, we see today the proliferation of a new species in the taxonomy of vertical flight. So good morning, ladies and gentlemen. We are gathered here today to discuss the potential impact of these revolutionary technologies and the impact that they will have on being able to transport ourselves expeditiously to and from our destinations. As we know, urban relates to the high-density ecological architectures that characterize towns and cities. Mobility relates to our movements within these constructs. But we envision, indeed aspire, that the added third dimension introduced by air will create new paradigms in transportation efficiency and convenience, and enable what hitherto has not been our prerogative. We have today with us 5 outstanding panelists from an outstanding cross-section of industry to share their perspectives on what the future holds. Karthik is with AQ by Airbus. We have Scott with Bell Helicopters. We have Andy with Aero, Empirical Systems. We have Mark Moore from Uber, and we have Chris VanBuiten from Sikorsky. Today's discussions, what I would really like to have our panelists cover is not only provide a little bit of an overview of the incentives and the initiatives that they are pursuing at their companies, but also opine on their perspectives on what air mobility and especially urban air mobility means, talk a little bit about early catalysts, not just one particular model, but other possibilities of early adoption that's related to urban air mobility. And I would encourage you as the audience to think about the same types of questions that you would like to ask of the panelists. It's wonderful to be in a panel or a session where everybody is of the same thought and same objective and same perspective, but to hear from the naysayers or the challengers is equally important to provide perspective to what we're going after here. So please don't be shy. As far as guidelines are concerned, very quickly, we have about 20 minutes for each of our panelists. They will speak in turn. I will make brief introductions to all of them before they speak. I would encourage you to use your smart mobile devices to submit questions. We'll take the questions in real time, but we'll address them and answer them all at the end of the session, give us a more interactive opportunity. So after everyone's had a chance to speak, that's when we'll take them, but please do upvote them if you wish to. It's anonymous, so nobody will identify who you are. If you want to ask a difficult question, feel free to do so. But before I get started with our first panelist, I just want to acknowledge Barry Lakensmith and Colin, our organizing champions here, who made this all possible. So thank you very much and welcome. Go back one page, please. You want me to do that? There you go. He's in the process of entering it as we speak, so let's give him a second. You good, Bill? Yeah. Okay. So with that, I'm going to introduce Karthik. Karthik runs Altiscope, a project of AQ by Airbus. He's working to help regulators define the rules, policies, processes necessary to enable large volume autonomous and unmanned flight in airspaces around the world. Most recently, he was co-founder and CTO of Coin, which was later acquired by Fitbit, a VC-backed digital payments and consumer electronics startup. He's worked with NASA Ames and Goddard, as well as the Aerospace Corporation on projects ranging from planet-exploring robots to launch vehicles. Karthik holds a PhD and MS in aeronautics and astronautics from Stanford. He designed and built advanced spacecraft technologies for the detection of gravitational waves, which we all know now exist, or have proven. And he has a BS in aerospace engineering from UC San Diego. So with that, Karthik.
So my name is Karthik. I run a project called Altiscope, which is one of the many projects at AQ. You may be familiar with VOOM, which is our on-demand helicopter service that's running in Sao Paulo. You may be familiar with Vahana. So this is a different project that I wanted to introduce you to today. So I want to start with a video. So this is the first video, just kind of our vision of what the airspace might look like in the future.
The dream of flying is as old as humankind. Today, our skies are busier than ever, with over 1 million people flying at any given time. By 2030, air traffic will increase more than tenfold as autonomous aircraft join existing traffic in the skies. But in order for this to happen, decision makers need tools to understand their airspace. In collaborations with government regulators, Altiscope is safely enabling new uses of our airspace through deep analysis, policy simulation, and decision modeling. Airports are evolving to incorporate new aircraft types and services, such as air taxi, autonomous package delivery, and autonomous cargo jets. In this critical coordination space, Altiscope is jointly analyzing the requirements for communication standards and operational risk thresholds. Manned and unmanned traffic serve many critical suburban needs, yet public concerns such as aircraft noise levels, personal privacy and safety must be addressed. Altiscope shows regulators how policy options affect their jurisdiction in order to support the implementation of data-driven policy. It's 2030 in Helsinki. Before a football event, a flight restriction is issued. Media drones receive permission to fly as their flight plan allows. All other flights are safely rerouted to their destinations. If an emergency occurs, emergency vehicles have priority. Once the restriction is lifted, traffic returns to normal. Realizing the social benefits of this future requires new policies that are carefully established through data-driven simulation and review. Altiscope is enabling policymakers, operators, service providers and manufacturers to build fundamental infrastructure that will scale aviation activities for decades to come. We're building blueprints for the sky.
All right, so this is sort of an introduction to what our project does. We're not building a UTM system, we're not building a vehicle. What we're doing is helping regulators around the world do the simulation, do the modeling, do the analysis of what the airspace needs to look like. So looking at the kinds of vehicles that you might see in a local jurisdiction, looking at the types of social constraints, looking at acceptable noise levels in a community, looking at a variety of things around safety and perception, and helping to figure these out in terms of what the airspace model actually looks like. And I'll go through some examples of these in the next few slides. But I want to start off with just what is the sky actually going to look like as we introduce these new kinds of traffic into the airspace. So I'm going to start with a graph. Sorry, guys. X-axis is years from now through around 2030, 2035. And the y-axis is the number of flights worldwide in log scale. So the orange is, so the bottom kind of the straight line that you see is commercial air traffic. So IATA predicts about 3 to 5% growth in air traffic every year. And it's pretty steady, driven by different countries as different countries grow at different rates. And just with commercial air traffic, you'll see about a doubling in the next 15, 20 years. But now add package delivery. So drones carrying packages, not carrying people. You'll see at least an order of magnitude increase in the amount of traffic in the skies. Now think about carrying people around, right? How often do you order something versus how often do you physically move yourself around a city or around a neighborhood? It's quite a bit more than that. So now you're talking about 1 to 2 orders of magnitude more than that. And this is not including induced demand, right? Induced demand is where you start to use a service because it's now possible to use it, where you start to take activities you otherwise wouldn't have done. If you think about induced demand, these numbers are probably low. So how do you enable these kinds of activities to actually take place, right? It's, we can think about, yes, let's just get all these aircraft in the air and see what happens. Maybe that's not the approach I think anyone in this room really wants to take. So this is a view out of our simulator of what projected traffic in the year 2030 over Paris might look like. And if you can just go to like the middle and pause it, so we can kind of take a look. Yeah, you can just pause it right there. So what you see is airports, Charles de Gaulle and Orly in the north and the south. You see some gray dots right next to the airport. These are essentially vertiports for bringing people in and out of the city to the airports very rapidly. You see some gray dots that are stationary around the city where you have lots of flights coming in and out. These would be package delivery hubs, for example, or ports within the city where lots of people are coming. And this, by the way, is just a small number of vehicles, right? If you look in the bottom left, this particular number is about 232 vehicles in the air at any given time, which sounds like a lot, but there's a lot of people in a city. So if you want to have vehicles that are used by the mass population, you may be looking at an order of magnitude more than that. So a lot of vehicles, and the driving factor here is essentially human air traffic control needs to evolve, right? Air traffic controllers go from tactical to strategic, kind of managing the airspace versus controlling individual aircraft. So we can go back to the slides. Or if you can actually pull up the video number 3. And this video is actually in the south of France, so in Bordeaux, so kind of similar to Napa in terms of, you have a city center, but then very quickly becomes rural. And even with this, with kind of the population densities that you see, you still see quite a bit of demand, right? People who want to go long distances, tourists who may be going from place to place, cargo that's being delivered from farms to factories, and geofence zones where farmers are crop dusting or surveying fields. So you still see a hub of activity even in more rural areas where you might not expect sort of urban air mobility to be the buzzword. So finally, I want to show video number 3. And so this is over a much larger area. If you can just pause in the middle so it stays up on the screen. So this is Tokyo, Japan. Much larger area where you have a very dense urban core and very quickly turns into much more rural, especially in the southeast area there. And what you see is still quite a lot of traffic coming to and from the urban core. These simulations, I'll talk about how we generate them, but are based on population density, they're based on economic demand, they're based on people's commute patterns today, sort of projected forward as a function of market share that might transition to these kinds of vehicles. So it's not us thinking just arbitrarily where might vehicles fly, but seeing demand shift from the ground to the air, and again, not really taking into account what induced demand might be. So induced demand by itself could be pretty crazy. So we go back to the slide deck, please. So how do we actually enable this? So the first thing is systems have to support local needs, right? If you start with the, I'll talk to this chart. The top boxes are different kinds of applications you might see in the airspace. So anything from the hobby drones you see all the way up to large commercial aircraft, right? So you're thinking about package delivery, moving people around the city, search and rescue, existing general aviation, existing rotorcraft activities, hobby, film, etc. For these to exist, you need supporting infrastructure, so air traffic management systems, communication systems, emergency management, emergency response. But the thing is, in order to build these, you have to actually have system specifications and system requirements. And the thing is, if you go to regulators around the world, there's an understanding that you need safety, there's an understanding that you need security, there's an understanding you need communications. But what is, for example, the communications latency requirement between the aircraft and the air traffic management system? How does that depend on the kind of application? How does it depend on the kind of aircraft, right? What is the actual security model that you're going to be using? How do you ensure that messages aren't spoofed? How do you ensure that today's unencrypted voice channel can still be used potentially, or how do you transition that to something that's encrypted for piloted aircraft? And how does that fit into a world where you have these hundreds of aircraft fitting around? And all of those rules depend on local laws, local policy, local culture. What works in one place doesn't necessarily work in another. So to give an example of this, imagine you want to go from a ship offshore to a building in the downtown core. There's two ways of doing this. You can fly a direct, nonstop route, or you can try and fly following a highway or a river. Which one is safer? Is it you follow the river, and if you have an accident, you crash in the river, and no one who is on the ground gets hurt? Or is it you fly the direct route, you minimize the time in the air, you minimize the probability of an accident happening because you were in the air for the shortest amount of time? Which is it? Well, it actually depends on what's locally acceptable. For some people, it's we want to minimize the total number of accidents and total number of crashes. For some people, it's we want to minimize the effect on sort of non-consenting participants. Which is it, right? Very local specific. So some key questions, and these slides will be available, but we look at safety, right? So if you have 200 vehicles in the airspace and you have a non-compliant actor coming through, how quickly can the aircraft disperse? How quickly can they deal with this person that's coming in? We look at security. So when you say let's add encryption, what does encryption mean? What are the threat vectors? And what does this mean in terms of the communications and the processing overhead that's required on the aircraft? Can you fit the equipment necessary to be secure enough for large commercial aircraft on a drone that's this big? Maybe, maybe not. And finally, economics, right? When you think about how you do deconfliction, how you do routing, how your sense and avoid systems actually work, they have very direct impacts on the economics of the airspace, right? If the shortest path is 5 kilometers, but the route that you're given is 7 kilometers, does that make or break your business, right? Do you have the margins to deal with that? And what does that mean systematically? So we do a lot of this kind of analysis for regulators around the world. So as a more concrete example, how close to your roof should a delivery drone be allowed to get? So you're sitting at home this evening, your neighbor says, I really need this package in 5 minutes, goes onto his app, orders something, and you hear the drone buzzing overhead about to land in his backyard. How close to your roof should your neighbor's delivery drone be allowed to get, knowing that the next day you might order something as well? Is it dependent on the payload that it's carrying, right? If it's a gallon of milk, because he wants breakfast the next morning, versus a propane tank for his cookout. Maybe it's dependent on the vehicle type, right? So if there's a million of this vehicle flying around versus the first commercial flight of this vehicle, that distance changes, right? Maybe it's based on the operator itself. So someone who's doing 1 million flights a day around the world can fly closer because they have a better safety record. But depending on how close to that roof you can get, determines and starts to impact the aircraft design as well, right? How you approach into the backyard, how quickly you have to be able to take off, the amount of battery that you need, now you start to drive the vehicle size. So what people think about as safety requirements, what regulators might think about as safety requirements, starts to become an engineering design problem as well. And you can very quickly end up in a situation where you've designed the safety in a way that you can't actually build the aircraft to effectively perform that mission. So how do we make sure that we don't get ourselves in that corner? So this is a lot of what we're trying to do. So another example here. So this is going to be some more graphs. We want to look at separation requirements. So if you talk to people around the world and you ask them how close should two unmanned aircraft get, do you use existing commercial rules and regulations, or do we come up with new rules and policies based on what these new vehicles can do? So we started looking at basically looking at the Paris scenario that I showed you earlier. Started to randomly generate traffic based on demand economics, and looked at if you kept different sizes of keypad zones around the aircraft with no deconfliction strategy, with no air traffic control, just said, hey guys, just go fly, what would actually happen in the airspace? And actually my email address is in the lower corner. If you shoot me an email, I can send you the actual document with how we generated this. But what you see is that at very low densities, and if you really care about collision, you can actually introduce quite a number of aircraft into the sky without really seeing too much risk. But as you get into higher and higher densities, that risk quickly climbs, and it quickly exceeds what you see with commercial aircraft today, which are the red lines for collision on the left and separation, loss of separation on the right. So the question now becomes, how do we take these curves and apply deconfliction strategies, air traffic management strategies to shift those curves below the red line? Or maybe it's a different line that we need for unmanned systems and for autonomous systems and for urban air mobility. So as an example, another example is detect and avoid. So we wanted to say, okay, if we take existing ACAS systems and we just put them on all the drones in the airspace, what's the actual loss of separation rate going to look like? And how does that actually perform compared to not having any kind of deconfliction strategy? And what you see on the left hand of this curve is the ACAS performs very, very well, which is what you expect, right? Commercial aircraft cities. But as the number of aircraft in the sky increase, you actually get into a situation where today's ACAS performs worse than not having any kind of deconfliction mechanism. Why is that? Well, I think part of it, and what we've seen is, as you try and avoid the aircraft next to you, you cause another potential collision with the aircraft on your right. It's sort of swerving on a crowded highway versus swerving on a highway at night to avoid a deer. You have to decide, is it better to hit the deer or to swerve, right? And so the question now is, well, not having detect and avoid is not really an option. So what should that system look like? So we work with transport planners to figure out on the x-axis where the densities are going to be for a particular community. Then you work with safety regulators to figure out, okay, what is the actual acceptable loss of separation rate or the acceptable collision rate? Then you can start to look at various options for detect and avoid systems, run them through our simulator, and say, are we actually meeting or in the ballpark of that point? So again, another example of the kind of studies we do with regulators is, we need avionics to build our aircraft and to actually start flying them. How do we set requirements so that avionics manufacturers have the data necessary to design against and the specifications to design against? One final example is around communications. And we'll have quite a bit more to share on this in the next coming months, so this is a little bit light. But again, if you shoot me an email, I'll be happy to send you what we have so far. Communication selection is driven by needs. And this is obvious, I think, to everybody in this audience, but a lot of audiences, when I put this up, they say, oh, you're right. It's depending on why are you communicating. Is it just sending out a beacon of who I am? Are you actually trying to control the aircraft from the air traffic control system? Very different requirements on bandwidth, on latency, on reliability, right? A beacon might be once a second, once every 5 seconds. Real-time control might be 10 or 100 millisecond latency with very low packet loss. What's the geography like? what is the vehicle like, right? The kind of satellite dish you might put on a commercial aircraft simply won't fit on a small drone. It's an order of magnitude bigger. So just because you have a requirement on performance doesn't mean you can physically fit it in. And finally, what are you trying to do with the mission? Is it manned? Is it unmanned? And what really comes out of this is that in a single airspace, you'll have to support a variety of architectures. When you're thinking about doing a package delivery in the same city where you have people flying around, in the same place where you have maybe the fire department trying to get situational awareness over a fire, you'll have vehicles using 5G, using LTE, using SATCOM, using a downlink, and then plugged into basically a wired connection, all trying to talk to the same systems. So how do you actually harmonize this? So we're probably the next couple of months we'll have some more to share here. And just wanted to show this geographically, right? It really comes down to a mixed equipage problem. It's not everybody speaking the same language. It's different people in different areas have different equipment that'll work for them. But what makes things more complex is think about transitioning from the top left, where there's very few aircraft and maybe there's no cell coverage, so you're using SATCOM, or you're just broadcasting your position and hoping that Sense and Avoid takes care of it. And then as you transition down into the urban area, where you have a huge number of aircraft using potentially different communication standards, right? How do you ensure interoperability? So this is another one of our efforts. So essentially, we're enabling policymakers, operators, providers, and manufacturers to build infrastructure to enable the next generation of aviation. So thank you.
On my videos, I think they're embedded, so if you just press play for me, we can make it through there without switching out. So I wanted to start today with a conversation about on-demand mobility across a space of urban, interurban on the bookends, and then also logistics in the middle, because I think it can go both ways, both urban and interurban. So on the intraurban side, we're going to talk a little bit about what you may have seen last week at CES. Bell presented their air taxi experience. And then on the logistics side, before the Christmas break, we released a family of vehicles that we call APT, Autonomous Pod Transport. And we'll talk about that vehicle in the logistics space. And then I think, of course, there's an interurban conversation that can go on. Bob is probably here with TriFan, and our friends from Leonardo are working Clean Skies too. And as you know, we're flying currently our 4th generation tilt rotor, although that's for Dr. Lewis and his crew. You can see that the technology's there for extending this out into the interurban space with transformative lift. So this is the first video. This is a little intro that we did for CES. So that was our teaser going in, and then when we finally got to the show, there was a mock-up of our cabin. So as you can guess, the first question everyone hits you with is, where are the flying bits? And my coy response in a place like this is that Bell Helicopter's been doing that part for a long time. We've got that covered, and we'll reveal it when it's good to reveal it, keeping our competition on their heels, etc. But what's this really about? And Ashish asked us to talk about this a little bit. It's about reaching a new set of customers. So having just the cabin there at CES sort of doubles down on that proposition of identifying new early adopters and getting the masses involved in urban air taxi. At CES, not everyone's bought in. Most of the people in this room are bought in. I bet if I had one of these out back ready to fly, you'd be lined up to take that first ride. I'm the same way. At CES, we were receiving questions like, well, what does urban air taxi mean? What does it do? Does it really fly? So that was a wonderful opportunity to meet folks like that and open up doors there. Then the second part is, if we want to reach the masses, and my grandmother and grandfather or my grandkids maybe, because it might take longer, if they want to get on board of a vehicle like this on a VTOL aircraft, that's normally reserved for elite military, elite customers in the commercial aspect. They want to get a sense of what it means to be inside of one. So you notice the trims in the teaser video. You notice the interface in this picture here. This is about feeling like you got inside a car or a airplane maybe that you flew in before. It's about making folks feel comfortable and then having an experience of what it's like to go from one place to another. So when you got inside, you not only had the visual and tactile feel of the interior of the cabin, but you put on some VR glasses and it picked up your profile from the check-in point and then took you to a gala event or a crosstown meeting or even a golf course. So we were trying to give them that sense of wonder, that sense of what mobility really means. If you noticed in Ashish's definition, that first part's the easy part. Yeah, we move people and things from point A to point B, but the second part was we do it freely and easily, efficiently. Well, that's what we want to give people a sense of by this experience. I described often when I was talking about this vehicle at the show that we have taken a few people, Mark and I went on a great ride on a 429 from Terminal B in DFW over to Frisco, Uber's hero route in DFW. We went at speeds that this vehicle would go at. We went at altitudes that this vehicle would go at. And we took what's normally a 1 hour and 10-minute traffic jammed ride on the ground and did it in 8 minutes. So Mark and I can geek out about a lot of things, but at the end of that ride, we were both kind of like, wow, this means something in our lives. It means I can be with my daughters more, you can hit the gym more, you can do more business transactions. It means something else. It means the second part of what Ashish described in the mobility category. So we're going to be around with this vehicle, hopefully at a few more shows. So if you get a chance, look for those schedules and come and experience this with us. We also had kind of the back end of it where you get in a simulated elevator and check into the flight. So it's part of the whole shooting match, not just the trip itself. So on the logistics side, we introduced this family of vehicles called APT, Autonomous Pod Transport. I'm so mad at the guys for changing it. You know, the first name that John McCullough and I came up with when John's the inventor of this, along with his friend Paul Oldroyd, it was AAPPT. I mean, it still spells out apt, but now you can add autonomous, all-purpose, you know, and it's just so much better. But Com's got the best of us and simplified it to APT. So this is a family of logistics vehicles that range from, let's call it small, medium, and large. Let's call it sub 55, part 107. Medium, we can tote around maybe up to 5 to 800 pounds. Large, into the thousands of pounds. And we've set it up in a very simple configuration. As you can see, it's a tail-sitting biplane. And if you do this right, you can do unicorn words like modularity of propulsion. One mission might require electric, one mission might require hybrid, one mission might require a gas-burning engine. The pod in the middle is very modular as well. You can envision it taking on any package you want, whether contained inside the pod itself or separately hanging between the pylons there. A lot of interest and a lot of fun parts. And again, Ashish asked that we not focus so much on the vehicles. We're always going to take a shot at that. But what have we learned here? Bell enters the space and says, we'll never go into that sub 55 pound range. That's not what we do. We're going to focus in that hundreds of pounds or thousands of pounds and see what comes out of it. But it turns out the most important voice out there wants all three. They want something that can do smaller. They want something that can do that medium. And they want something that can do the largest. And that's whether it's the military and the logistics missions that are out there, or the commercial folks that want to deliver packages or even do retail deliveries as well. So it looks like that's the gateway, that's the entry point. So you're about to see a video on the small side of how this aircraft flies, and I think you'll see the power of it. It's tactical, it's able to land in urban environments because it's VTOL, but then it gets on a wing real quickly and gets you your package when you need it. So we just converted to airplane mode, do a once around in airplane mode, and you'll see her come back down and land. And again, what I think is interesting about this is back to the second half of the definition we talked about in mobility. So mobility in moving things from one place to another is one thing, but easily and efficiently. So if you get wing-borne, the easy and efficient really starts to make sense. It's about the speed of delivery, the distance of delivery, and a vehicle that can do edgewise flight and wing-borne flight, in our opinion, is the answer to that equation. This was out on Bell's property and under Part 107 rules. Another interesting point, just thinking about that vehicle. In the early days, when we were keeping on-demand mobility as one word, saying we can move things and people in the same vehicle, and we thought maybe that was it. Maybe that's better for logistics. You see the Spartan nature of that vehicle. Perhaps a fun ride too fun of a ride for passengers if there was a pod in there that rotated on a gimbal and came forward and aft for CG management. But there may be folks that want to do that mission as well. So that vehicle is there to answer that too. And then you see now where we're headed on the CES side, on the air taxi side, excuse me, where it starts to become more of a consumer digestible version. So we were also asked to talk about a few challenges. All challenges are opportunities. These are 3 new tech areas that I'd like to focus on a little bit. We typically talk about transformative lift being, powered lift being one of the things, flight controls being another thing. Now you've got controls and propulsive effectors all in the same, certification, autonomy. But I've picked 3 different ones because everybody here in this room is familiar with the others, and you're probably familiar with these too, but I thought it would mix the conversation up a lot. So first challenge for us is let's get this digital fabric right. And so you see right away, it's not just a thread. So I'm going to show you a video that looks like just a thread, but it's the digital fabric that we use to get the V280 from the drawing space to flight in a record amount of time. And if you listen to the video in the right way, you'll identify that this is truly a fabric, because it not only touches engineers to the manufacturing floor, but then it extends to our customer. And if we apply it again into the urban air taxi space and the logistics space, you'll see that it threads in those same ways and creates that fabric on the operational and OEM side. And then the digital fabric of the experience inside the vehicle itself. So now, when the customer gets inside of the vehicle, there's a connectivity. And suddenly that digital fabric becomes, it's a vehicle on the Internet of Things. So now you're having a meeting on your way, interfacing with your fellow passengers, or discovering what's important about where you came from and where you're going. So and that's the key, that key endpoint is why I bring it up for this group. So several thousands new paradigm for Bell, air taxi, several thousands new paradigm for all of us in the VTOL space. So in order to not only produce those vehicles at those new rates, but then maintain them. We want to operate at 2,000 hours per year. Did you hear the voice of those operators, how excited they were to have a tool like that? That applies now to on top of the vertiport, on top of the pickup location where your unmanned logistics vehicle is, or out in the field in the military, or at various airports for larger aircraft. So as these rates go up, if you make that digital fabric one of your priorities, you can really keep this energy going, this momentum going. Another challenge I wanted to talk about was the NAS. PK covered this wonderfully this morning, but Bell's starting to focus on it more. Obviously, it's a big issue for this as we move forward. And here's a quick map from our application into the UAS IPP program. So Bell has joined with the state of Texas and all the adjoining states of Texas to form up a team called Team Talon. Uber is a part of that team as well, and the Lone Star COE down in Corpus Christi. The red shows some of the routes we'd like to open up. So if you look at what these are, You go upper right from your perspective, that's in and around the Alliance Airport. If you've ever been up there, it's loaded with logistics warehouses. So how do we get from there into key, call them urban points, whether it's the airport or one of the surrounding cities? Then take a look, try to get straight across from Fort Worth to Dallas, a wonderful route not only for the intra-urban discussion, but it could be the start of the inter-urban discussion as well. And then the Uber Hero route, a little bit of the long way. We plan to connect that a little bit better up to Frisco, but that's essentially that spine road there through the DFW airport that Mark and I and others have taken to feel that wonder about moving things from one place to another at greater speeds. So we're really excited to be a part of that program. Hopefully we're in a winning position. I think there's only 5 spots on that pilot, but Team Talon is a very strong team, I believe, and these are the kind of things we're going to work on as far as airspace goes. And then the next one, reach the masses. So again, it's about folks that have never been in vertical lift before, so we have to produce at scale. And I've talked about this before, and I said, well, we need cellular mechanized manufacturing. It's not automobile F-150 rates at $750,000 a year. It's somewhere in between in that boutique range. Well, I pull in a new slide, and I want to talk about this in terms of 2 mistakes we always make in this industry. I'm saying synthesis of rapid prototyping and production. Well, what goes wrong in this conversation? One goes wrong when we're overly optimistic, and one goes wrong when we're overly pessimistic. So let's see if we can find the balance. We're always overly optimistic when we prototype a vehicle or demonstrate a vehicle by saying, that's our production vehicle. That's our certification vehicle. In my experience, and probably in yours, those vehicles have some change to go through because you're learning the most about them as they're flying and operating in the early days. On the negative side, you always say, well, duh, Scott, we don't use the same tools that we use in prototyping, that we use in production. We don't use the same machines to do that. So on both of those, I say, well, why and why not? On the side of going faster and reaching more customers, that initial vehicle's closer to the final vehicle, can we do better there to make this synthesis make sense? Can we get that vehicle closer safely, but closer to the final production vehicle so the experience wheel starts early and the adaptability starts early? Then on the other side, well, if rapid prototyping is kind of your glory days of the whole thing where, oh my gosh, we did this vehicle in 2 or 3 years and it's out flying, look at how great we were, why would you all of a sudden let go of that and not apply those same rapid, agile movements to your production? Hence the cellular mechanized, machines doing different tasks, operators being able to, or manufacturing, floor folks being able to do different tasks. So here's a couple pillars of the talent, your processes and procedures, and then a good mix of your internal and external capability. And then the final one is the business model. We've talked about this one before, but I've expanded a little bit. There's opportunities as an OEM. That's obviously where we are today. But what about Bell being an operator? Can we do that? Can we maintain a vehicle that we designed better than someone else? Can we service or fly those vehicles better than someone else? So we're having this discussion internally. It's a hard discussion, as you can imagine, because it's a whole different sector of the marketplace. But it's very interesting inside this urban air taxi model when you know that you're trying to maximize the dollars that are in there so that everyone can join in. On the booking engine side, Uber's got that covered, but it was an interesting, and others, but Uber's got one of the best setups for it on the ground, and we believe it's going to get there in the airspace too. But that's where we started to say, we stay out of that. But what we did is we started to list things that we do or do together across operator, OEM space, and booking engine, and you find these wonderful moments of synthesis again that you ought to start to discuss things with each other. So the OEM skills carry over into operator skills, carry over into some of the booking engine skills, and that's why ecosystems like we're discussing today and throughout the week are really important. Final slide. I've done a lot of these tours and talked to many of you in the room, but I wanted to introduce some new folks on the team. There to my left, I guess that is Carrie Cannon, the new chief engineer of Bell Innovation. Carrie, if not is one of the best development chief engineers at Bell, and I'd put him up against anybody in the industry as well. We're thrilled to have him. Think Fire Scout, think Eagle Eye. Mike Ryan's there next to him. Mike's the lead of our urban air taxi project. Kyle Hieronymus, far right to me, is here as well from the propulsion side. Please reach out and talk to these folks this week. They'll be with you all week to discuss potentials for partnership, working at Bell, or otherwise. Thank you.
So I realized when I looked at the list of everybody on the panel, everybody up here is a billion-dollar company. In some cases, tens of billions of dollars, and we are not. So we are a very small company. While we're here, we've been focusing on airplane development, electric air vehicles for over 10 years. We actually started backwards on large transport aircraft, turboelectric, distributed propulsion, superconducting electrical machines, and have slowly transitioned that to the vehicle you see in the middle. It's one of our flagship vehicles. We call it the Eco 150. It's a non-superconducting, conventionally cooled electrical machine, distributed propulsion vehicle, and that's split off into two different efforts over the years. And you see an approximate timeline at the bottom. That spun off into a project called Leap Tech we did with Joby Aviation, very well documented, which has led to the X57 Maxwell, for which we're the prime contractor. And then on the top, a lot of work on hybrid electric rotorcraft. So we began to pivot once we really realized that electric propulsion is real for conventional electric machines and for VTOL operations. So I'll be talking today about some of the design and its enabling technology from working hybrid electric rotorcraft and electric VTOL rotorcraft design, and then kind of talk about the hardware and give an update on the X57 and where we're at today. So when you start the design process, and 10 years ago, the component databases didn't exist. The various vendors that are working components didn't exist. So knowing your supply chain, knowing your components are critical even early, very on in the design process, as they're going to drive your integration, which I'm going to show a little bit of, but it's also going to drive your design, significantly drive your design. So once you have a good understanding of your components, and of course, now that vendors exist, you can begin to fill your database with physics-based models for electrical motors and things. You start to do the notional design of your configuration, right? And for electric propulsion, it's all about the payload range. Is the propulsion system actually buying its way onto the airplane? In many cases, it doesn't. In the case of Uber, it does, because you're cutting into range, but you only need 50 nautical miles, or you only need 100 nautical miles. And then you begin to hybridize. So you see over there on the left is just payload range for various battery densities, kind of see how that affects your payload, fairly straightforward. Then you start to look at hybrid propulsion tilt rotors, and all this work was based on a hybrid electric XV15, which I'll show. So I'm glad Graham showed a XV15 this morning, because it kind of set the stage for that a little bit. So for the hybrid propulsion tilt rotor, just looking at the payload range for conventional architectures, propulsional, just turbine-based. Then you start to look at things like battery assist, essentially a parallel hybrid where your battery is not necessarily sized to take all of the flight loads, flight propulsor loads. And then I believe there's a all battery configuration there as well. Then you go to the right, you start looking at future hybrid helicopters or future hybrid tilt rotors. And this is really where you start digging down in your design, and you're trying to assess your technology. Shown here are 15, 30-year curves on a payload range for the hybrid electric XV15 as the example. So you begin to really look and know where your battery is going to buy its way on the plane. Turbines aren't getting much better in the next 30 years, and maybe somebody from Pratt would shoot me for saying that. But where it becomes transformational is on the electric propulsion components. When energy density gets better, when batteries get better, that's how you're creating these transformative concepts, and why we're here to discuss this. Then once you understand your payload range and you begin to get your configuration at least sketched, you really have to dig into your mission planning and your energy management. You're no longer worried about fuel remaining on board in an OEI condition. You're worried about how much energy do I have on board. So on the left, you see just various ways that we're moving power around the airplane. In the middle is where you really start getting down into the weeds and really trying to understand your trade space. So that's for a tilt rotor configuration at nacelle 0 and nacelle 90, where you're at for an endurance indicator and a range indicator. Really what these are specific endurance and specific range equations, which we've completely modified for electric VTOL. You really throw out all conventional design equations for electric air vehicles. So essentially you can imagine for every different nacelle point through transition, and right, V-22s will cruise around it 30 or 45 degrees tilt. They do it over the Central Coast all the time. Where does that fit? So you begin to create a carpet plot where you can compare both propulsion architectures for a given configuration, but you can begin to also assess configurations against each other, and that's kind of, for the tools we have today, how you can begin to assess your design space. Then on the upper right, really kind of an eye chart, but what you're dealing with there is your energy management. Right, if you lose a motor, if you lose an engine, what's your energy on board? It's no longer a function of fuel, it's a function of how much energy is in my propulsion system, how much kinetic energy is into my vehicle, and how much thermal energy or thermal capacity do I have remaining in my components. So with the electric propulsion, you can push them beyond what you can turbines in some cases. You can push your motor to 150%. On the case of X57, we can push our controllers to almost 200%. So you have this capacity to really push beyond what the conventional turbine can do. So your OEI case is no longer 50%. Your OEI case could be 75% or even still 100% for a very, very short period of time. So while you're going through that and trying to understand the trade space of your design, you also need to be trying to cram your components in. So this is just kind of showing 15, very well documented airplane. We were able to get our hands on enough drawings to begin to adapt an electric propulsion system to it. So you just see some iterations in the nacelle design that we did there. Batteries are just located in the fuselage. This will be covered by Bree Danis on Friday in a panel. He's on the hybrid VTOL panel. He'll be digging into these performance charts a little more and what it means for mission planning and kind of how you treat that during the conceptual and preliminary design phase. So while on space claim challenges, we'll talk a little bit about X57. You see here the X57 Cruise Nacelle, where we have the Joby X57 Cruise Motor controllers are crammed in there. Those controllers are overperforming very, very well to where a single controller will actually run the full power of the motor. The Joby X57 is out there on the tip. You see a picture of the hardware there, and then some of the instrumentation equipment we've designed in the back there. For those unfamiliar with X57, it's a NASA X-plane of which Mark Moore is kind of the father of before he left NASA to go to Uber. So we're trying to not disappoint you. We're in the middle of Mod 2 right now. Actually, tail end of Mod 2 airplane will be flying this year. We have the Mod 3 wing under development. You see it on the top. That's the high aspect ratio distributed propulsion wing. And then the conventional Tecnam retrofit will fly again this year, where Mod 3 will be integrated and built also this year, getting ready for flight in 2019, just down the road in San Luis Obispo, California. Traction bus, just quick notes on the traction bus. It's a dual redundant traction bus. There is some work going on solar airplanes, et cetera, that are trying to certify that are treating their bus almost as a wing spar, just no redundancy built into it. So there's lots of different approaches for how you do your bus, how you do your battery management. And it's a space claim challenge as well in trying to fit your traction bus, in the case of X57, in a conduit that literally is about this big for a 3,500-pound airplane. So it's quite the design challenge, which you have to have very good knowledge and work very closely with your vendors. That's custom wire we've created for X57, showing up there on the upper left. We took some commercially off-the-shelf things and worked with a vendor to modify them specifically to fit our volume challenges. I mentioned the X57 Cruise Motor, designed and built by Joby Aviation. You see that on AirVolt test stand out at NASA Armstrong, and then the prototype you see there shown on the bottom left. X57 Cruise Inverters. So Joby worked with a company called Qtasys in Italy to design these. We've taken the software and validated and verified all the software for man-rated flight. I believe in NASA it's S1 rated software. I forget the exact, but it's the highest possible rating for software. That motor controller software just went through and passed verification and is ready for flight as of last month. And then you see some of the pictures of the hardware there. It's also gone through some initial environmental testing, passing that, and it's going through flight qualification right now. And I should mention the Joby Motors also went through endurance testing on that NASA AirVolt test stand, passed with flying colors, going through final qualification testing for flight. The Mod 4 version of the airplane, which now has funding, will proceed through 2020, and that'll focus on the high lift distributed electric propulsion system. So that will be the series of leading edge propellers on the wing. So you see some early design work here. We're starting to look into some early design for manufacturing. Joby and NASA Langley had worked very early on, some very early concepts on this. So now it's kind of our job to take those designs and push them forward into manufacturing, or work with vendors to push it forward to manufacturing. That'll be happening this year. Okay, flight batteries. We're going to get into batteries. I saw one of the questions that popped up was about noise. I think the batteries are one of the other most important things to enable on-demand mobility. Our early battery design was designed to meet what the ASTM standards are going for now. There's a lot of work within ASTM, SAE to define the standards for these flight batteries. And it failed. Destructive testing in epic fashion. So going to show a video of that, if you could hit it for me. Hopefully volume's on too. So keep in mind, this is all safety features turned off. There's no fusing on the systems, and the battery management system's disabled. So that's one of 8 packs that's going to go into the X57, about a 55 kilowatt hour battery, which is actually smaller than a lot of the battery systems that would be flying around in a 100 nautical mile eVTOL. So the battery, the failure we had here was actually in the Teflon burst disc, did not fail at the specified rating. And that is not something we had taken through or worked with EBS to take through any sort of qualification. We kind of just took the spec at the spec's word, right? And it led to an overpressurization of the case, which caused the batteries to run away significantly faster than they should have, which led to a whole bunch of sidewall ruptures in the cell. So very, very interesting. Really kind of drove us to control cell-to-cell propagation, thermal runaway. That was not the case for this battery design. So the batteries are a major issue. Uber's really working to push that forward. They've brought on Tesla's battery expert to kind of bolster this entire community and address, so this does not happen, so you're not sitting on this battery when it goes up. So X57's gone through a revision, and I wouldn't show you the bad video if I didn't have a good one, which is very uneventful, thankfully. We went through and redesigned the entire battery system at the same packaged weight as the previous battery system. We've now split the system up into 16 battery modules instead of 8 like before. So this has about 600 cells in it, 300 cells in it, I forget. So this design was destructively tested just right after Thanksgiving in Logan, Utah. At EPS and Utah State have stood up a new facility called the Blast Lab, specifically to do eVTOL battery testing. So I'm going to start the video on the right, which it'll start from the clicker. You'll see a small puff of smoke come right out of the scat tubing, because it turned out there was a little pinhole in it. Camera view will change here in a second. You'll see another little poof of smoke, and that's as eventful as it got. So that was a single cell going. And in the top video, you can actually see it, some adjustment, but you see that cell heating up and actually going into thermal runaway, and not propagating to any of the adjacent cells. One little puff of smoke, you continue your flight and move on with your day. So very high performing battery system. about a 30% package factor. And NASA featured it as a major milestone at that web URL there if anybody wants to try and type that sucker in. So ES Aero is fortunate to be working on both ends. We've been working on the transport concepts with our Eco 150, but we're really cutting our teeth and pushing forward with hardware as well in the transformational concepts, which is where the eVTOL is. So in these two areas, there's going to be a convergence. Anybody who's seen these charts, seen me present these charts at AIAA, for example, that green line keeps getting longer because the work that's going on in this space is driving these two areas to converge much sooner. And I think we'll see a 9 or 19 passenger parallel hybrid transport here in the 2025 timeframe. So we're really kind of pushing to that with the component integration work that's going on here, which is really driving a lot of component design and development work on the higher end on megawatt level machines, 2 megawatt level machines. So on that note, I have Mike Hirschberg's permission to plug the EACH Symposium, the Electric Aircraft Technology Symposium. This is very component based. It's not going to be VTOL specific. It's not going to be transport specific. It's a collaboration that AIAA is doing with IEEE. I'm one of the technical co-chairs for it. Phil Ansell from UIUC is the other one. Contact us for information on how to submit an abstract if you have a propulsion technology that fits under one of these 3 areas. Or if you just want to come learn about it, sign up for it. And the conference is in Cincinnati, so all the major aerospace propulsion companies are going to be there presenting their work in electric and hybrid electric propulsion. For sizes larger than what we're really talking about here, but still the industry is going to push that direction and begin to converge. So that is in, good question. Yes, that's in July after the AIAA Propulsion and Energy Conference. I believe it's the 13th and 14th of July. So with that, that's all.
Thank you.
Yeah, if you know me, all I've done at NASA is work on VTOL design and technologies my entire career. It's what I know and what I love. Also, if you know me, 32 years at NASA has made me very much a collaborative kind of guy. And now I've been at Uber for 1 year. And I have to say, I love the strategy that we've implemented at Uber, which is a very collaborative ecosystem building approach. We know we can't do it all alone. That's why we've gone to the experts in the industry to build the vehicles. We don't have that, maybe what some perceive as that Silicon Valley hubris, where we think we can do everything and don't really realize how hard hardware is compared to software. So, you know, it's a multi-billion-dollar initiative to build this urban air mobility solution for urban areas. And it is literally going to take a village or a new ecosystem to pull it off. So I'm going to give you a quick take about Uber Elevate, which is our initiative for urban air mobility. And I'm just really going to give you a very high level because later in the week, our Chief Product Officer is coming in Wednesday night to give a keynote. Thursday and Friday, we're very actively participating in the panels across all the topic areas. And Rob McDonald and I and also John Badalamenti are giving discussions on eVTOL tool framework, the vehicle research that we're doing and development, as well as the user perspective concerning this market. So you'll see a lot more from us over this week. So right up front, in a nutshell, what we're talking about is being able to, in densely populated urban areas, provide a new transportation choice for cities and users. And this is especially important if you look over the next 20 years. The projections on the ground are horrendous for these major metropolitan areas, and the projections are that these cities become much larger. So giving cities a new option to increase their productivity is very important to us. And again, as Scott pointed out, this is a flight that We've flown with Bell on their helicopters. Our hero route is to show that we can do this, what would be an hour and 10 minutes on the ground, 8 minutes in the air. And what's really important, because I've lived through kind of the peaks and valley of aerospace, and if you look back at 2008, 2009, when many companies were taking on the VLJ market, the very light jet market, and what they called air taxi. One of the things that I saw as I was looking across that, and had a good friend of mine, Bruce Holmes, who most of you know, go to day jets. The thing I didn't understand was how they could be economically profitable, right? Because they were, if you look at their business model, they were operating over, for instance, all of Southeast Florida and Georgia, and essentially had a 800-mile diameter of operations, with only a few hundred aircraft servicing that. What's so great about urban air mobility as a future service and product is that it has fantastic trip density. That is, there's lots and lots of people in a relatively small space to achieve great economics, right? Great load factors, very low number of deadheads. And that's what the very light jet market just didn't have, high trip density. So as they tried to implement flying an average load factor of 1.4 passengers around with 2 pilots in an aircraft that was optimized to fly at 40,000 feet, which never got above 18,000 feet, and was designed to fly 1,000 miles, but the average stage length was only 200 miles. Really fundamental mismatches between what the vehicle could do, what the business model said it could do, and really, from my opinion, didn't have a chance from the start. And I can tell you, I really understand. One of the things that really impresses me about Uber is they've gone into incredible depth on the economic modeling to understand that it is a pragmatic business case. And I will tell you, this is not a moonshot. We'll never let it be described as a moonshot. It is a product development effort that has a lot of complex engineering, but is very much focused on a product and a user experience that we care greatly to provide for our 65 million active monthly users. So here's a little video that kind of introduces you to that user experience. And again, this highlights that it takes a village. We highlight Hillwood on the door, if you saw that. One of our real estate partners for Dallas, Fort Worth area, who is taking the initiative to make the skyports real. You can see a representation of one of the vehicles. This is our common reference model. Most of our partners have not shown their vehicle, so this lets us show a vehicle to show a representative vehicle and what users should expect. We've done many surveys. We'll do many more surveys and share those with our partners, so that all the way through, as we build this ecosystem, we can be designing it for profitability, for good economics, for a good user experience. Certainly that means many different things, whether it's the vehicle, the airspace, the skyports, the regulations. All of these things have to come together in a highly collaborative ecosystem. None of us are going to do it by ourselves. So if we really want a feasible market, the sooner we start working together, the better off it is for all of us. So you can see highlighted, we have 5 different vehicle companies developing flight demonstrators. For us, it's really important to have several successful manufacturers and not just pick one favorite. It's very important to have many real estate companies engaged and pushing this. Our role is very much going to be focused on the airspace and the network management system and achieving a very, very efficient network, because you cannot do this well unless you really have high a well-engineered, highly efficient network that encompasses both the airspace and all those issues, as well as the network management and connecting to the user really well. So this is a little bit more about one of our common reference models. We actually have two different common reference models where we're openly sharing this geometry. The intent is not for us to build it or anyone else to build it, but to rise the tide for all of industry, all the vehicle manufacturers, to better understand these eVTOL aircraft, because they have really significant challenges, and there's much learning to take place. So 3 of the areas where we're committed at Uber to improve the state of the art and close technology gaps are: 1, on the energetics. You've heard that we've just hired one of Tesla battery leads. We're going to be very, very active in developing a battery system that's capable of 300 watt-hour per kilogram at the pack level and achieving the specific power of about 3C discharge that's required both for the recharging and the discharge in peak times. So energetics is a key place where we're going to help close the technology gap. Another, so it's really important to understand the energetics of these vehicles and to be running these kind of models through missions and understanding the reserves and other aspects of the energetics really well. Another key part that we're going to help close is very low community noise. So that's probably the most significant challenge that we have, to be honest, where we need to be pushing these vehicles at least 15 dB quieter than helicopters today. And so you can see some of the technologies that we're looking at helping to promote and work with others with the stacked co-rotating propellers. Not counter-rotating, but co-rotating propellers. So NASA and we are both very active in developing data sets which we can share with industry partners to promote ultra-low noise, high figure of merit solutions, such as those lift plus cruise propellers. The third area, so energetics, low noise. The third area is, it was mentioned earlier this morning, transition flight, right? It's not so hard to hover, it's not so hard to fly forward, it's really hard to transition between those two states. So we'll be taking one of the common reference models that again, we've openly disseminated, and be doing wind tunnel tests so that we can build databases and prove that the tools that we're developing and others are developing are accurately capturing the stability control and other transition problems. So again, we feel it's really important to rise the tide of understanding of eVTOL. So we've encouraged NASA to also share common reference models, and we encourage, in fact, all of industry to come together to lay a long and great foundation for electric VTOL aircraft. So just closing it up, again, you're going to hear a lot more about Uber Elevate throughout this conference, and really, really appreciate the leadership of AHS. They have been in on this from day one, as I was at NASA and trying to struggle to push this forward. Just cannot thank Mike Hirschberg and AHS enough for being seeing this new market and opportunity develop. Thank you very much.
We really appreciate this opportunity to share a Sikorsky perspective. This is really exciting. You are all pioneers, right? We're at the tip of the exciting beginning of this journey, and this is going to happen. And the leadership that you're all exhibiting by being here and to Mark's point, collaborating and having this discussion is what's going to make it happen. Let me just give you my bottom line up front. This is absolutely going to happen. We could talk about when and at what scale, but it's going to happen. And my opinion for that, or Sikorsky's opinion, is informed by building the Firefly demonstrator in 2010. And the big thing we saw in Firefly, the battery technology wasn't there at the time, but that picture there shows all the parts we took off a conventional helicopter. I just told the team, as you take each part off, lay it on the garage floor. There is nothing that I've ever seen that can so dramatically simplify what a helicopter is. And that's going to be super important to, one, we heard about the economics earlier, and two, I'm going to spend a lot of time talking about safety and creating a new benchmark in safety. So I think the electric flight is absolutely possible, and we saw some neat results on the improvements in energy density and things like that. The other thing, if you're in this room and you're passionate about being here and you have not flown a helicopter off a rooftop in Sao Paulo, Brazil, you need to. It's absolutely perception changing. The first thing, you depart from your US-centric view of the world and stand on top of a high-rise. In Manhattan, you can see the edges. Sao Paulo, it is skyscrapers as far as you can see. So you have to have that experience. Then you also have to get stuck in traffic in Sao Paulo, Brazil. And then you fly rooftop to rooftop and fly over sections of the city that have more vertiports than bus stops. And you'll understand that the infrastructure challenges are surmountable. So that just informs my opinion very much. And then what I'm going to focus on today, we're flying it at Sikorsky, we think the autonomy technology required. And I really like that the panelists have kind of, whether architected, masterfully architected, we're each talking about different pieces of the problem. We're flying the autonomy technology that would let any of you press a button and move safely through national airspace from one spot to another in a very complex helicopter at the required levels of safety. I'm a huge proponent, we've got to come up with a name for it, but the Newman criteria. Dan Newman, tech fellow at Boeing, last year at the joint session of AHS and AUVSI. He's like, I just want to sort out the wheat from the chaff here. If you're working on a new platform that you're not ready to put your family on and have them fly on it every day, if that's not what you're thinking about, you're working on a toy. If you are architecting your product from the beginning and you're thinking about a clear path to your entire family going on board the system and flying every day, and that means leaving from the 60th floor of a high-rise building in an urban environment, then you're starting to think about making an aircraft. And this is important, right? We all are taking on a commitment as we start this journey to work to the highest levels of safety. There are many industries that have had an incredibly bright future and had it wiped out by some premature early mistakes that in this case could have very high visibility. And I think we as a community have to collaborate to make sure that doesn't happen here. So Sikorsky perspective, I think you've seen different versions of what are the elements in the system. And for us, the vehicle, I'll be KG2. I won't share my opinion of what the ideal vehicle is. The electric drive is maturing in multiple industries, the energy density. I'm going to talk about the flight controls, the click and fly, move me from here to there in the safest possible way. We're also doing a lot at Sikorsky on fleet optimization, a couple thousand aircraft operating around the world, and we do a lot to monitor them, assure their health, and optimize their functions. And then the airspace and infrastructure, not Sikorsky, could be pieces of Lockheed Martin, but not the focus of my talk today. Let's just look at some simple math. This is the S-92 helicopter, FAR 29 certified, won the Collier Award for its advancements in safety features, right? Designed to be from the start the safest commercial helicopter in the world. It flies 19 passengers, has 2 crew up front, demanding offshore oil missions. Incredible level of certification testing. It can be struck by lightning. It can fly in high intensity radiated fields, right, that our urban transports could easily fly in and out of. The dynamic components were gouged with a special tool to put large defects in them prior to their fatigue testing, so it can fly with damage during its life and make it through a certification period. It's designed with 9.9 systems. It has a lot of DAL-A level software. And when you integrate, it has components designed to the 9.9s we talked about. When you integrate that all together, you get a fatal accident rate approximately of 1 per million flight hours, right? And that's essentially the benchmark in the commercial vertical flight world. 1 loss per million flight hours. That's an exceptional result. That's a Collier Award-winning result. It's not good enough for urban mobility. When we have 50,000 vehicles flying 3,000 hours a year, simple math, that's 150 million flight hours a year. And we saw different projections, right? Different numbers came up at 150 million flight hours a year, and that's what success is going to look like. That's what we all aspire for. We'll lose 150 machines a year. I argue that that's not acceptable. That's not close to acceptable, because these failures, take it from Sikorsky. We had a Sikorsky helicopter come off the Pan Am building in the 60s in New York City. And that we were running airline services, intercity out to airports. 161 rolling off a high rise and landing in the street ended that business almost around the world for decades. If we as a community build these systems and periodically have them roll off the top of a high rise and land on Fifth Avenue, I assure you we will not enjoy the success that we're all looking for. So how do we design these systems for the highest levels of integrity? This has been kind of the Sikorsky strategy for this particular piece of the autonomy. Building on a tremendous pedigree of fly-by-wire helicopters, we launched a 6-year program to mature the fundamental technologies to enable a non-skilled pilot to press a button and be delivered to another spot. And I like how the Lieutenant Colonel talked about breaking complex problems into pieces. We didn't take on the vehicle piece. We used some of the safest existing helicopters out there and added the autonomy to them to demonstrate this capability and mature the technology. We're 6 years into that. We partnered with Graham and DARPA on the Alias program, and we think we've fundamentally demonstrated the technology. There's still work to do. We're filling in gaps, but after that 6-year effort, we think that the matrix technology we have can, at the required levels of safety, enable that simple operation of a helicopter in complex national airspace. Talk is easy. We've demonstrated it. We've flown a couple hundred hours. It's now time to certify and qualify it. And that's what some of our DoD panelists talked about this morning. We intend to transition that technology to existing helicopters. The S-92, the safety benchmark in the world, and hopefully the Black Hawk, of which there are 4,000 around the world. These helicopters are unique in having an outstanding safety reputation. They operate in incredibly obstacle-rich, complex environments, bad weather, hard, unforgiving weather, running in the North Sea in a winter storm out to offshore oil rigs, very unforgiving environments. So we intend to insert the technology, develop a pedigree of certification and qualification, and then put on high utilization on these platforms. And don't wring out a new vehicle and new autonomy software together at the same time, and new propulsion. But wring out the autonomy system on very proven helicopters and move from 1 failure per million hours to 1 per 10 million hours. Even there, that's 15 accidents a year, but it's not 150, it's 15. You can argue whether that's going to be good enough. But we can fundamentally change the safety of helicopters that are flying today, the safety of people that are defending the nation in the Black Hawk, getting energy, flying S-92s out to oil rigs. So we can get a lot of benefit, mature the technology on those platforms, and then have the pedigree and substantiated data, flight experience to transition and enable urban mobility. We've architected these systems from the beginning to accommodate different vehicle sizes. You're all currently falling into 3 buckets. I've given this talk before, and I've talked to people afterwards. At least half of you, we're in Silicon Valley, probably don't have the aviation scars that I have or Sikorsky has. And you're like, what are you talking about? This is easy. I can solve this problem with my cell phone. And if one cell phone won't solve it, 4 will, right? I'm all about software. I got this. You're a laggard, going slow, what the heck? And then some of you are in the middle, and you're saying, oof, I think I got this. But yeah, that family on board criteria gives me pause. And then, some of you, your opinion might be modified by not having kids, right? That'd be interesting. And then the last are, the Dan Newman criteria is right. Fly my family every day is the criteria. We've got to get to a fundamental leap in aviation safety in vertical flight, get to at least 1 per 10 million hour level of fatal accident, which is just tremendous, and which can be enabled by the new technologies we're talking about. The autonomy, the simplification of electric propulsion, the airspace integration that several people have talked about, can actually achieve that kind of rate and actually enable this fundamental leap in the number of vertical flight aircraft that exist in the world, and the safety, the defense and search and rescue and life-saving benefits that'll come from that. Thank you for your time.